Okay, so now we just found an interval where we thought that the results might end up. So in that previous example, we knew the probability of success, P, and we were estimating what the sample would look like. So the sample is sort of the collection of running the experiment a whole bunch of times. So we knew what the probability of success was for a single spin, and we wanted to estimate what a sample of a whole bunch of spins would look like, what the proportion of successes would be. Now, that's not really what statistics does. So statistics does the reverse. What you have in statistics is you have a bunch of data. You have a sample, and you know the proportion of successes in the sample. What you don't know is P, the true probability of success. So statistics is going to say, using the data in the sample, we want to basically guess P. So we want to estimate P and also know how accurate that estimate is. So as we saw in the roulette example, like the more sort of trials there are in your experiment, the more data there is in your sample, the closer the sample proportion is going to be to the real proportion. You know, when we only played 300 times, the proportion we win could be well higher than our chances of winning a single spin. It could be solidly over 50%. But when we did 100,000 times, the proportion of wins was going to be like within like less than 1%, like within like 0.5% of the true proportion. Yeah, what was it within? Yeah, but within 0.5%, less than 0.5% away from the real answer. So basically, the bigger your sample, you know, the more trials there are, the more pieces of data there are in your sample, the more accurate your estimate is going to be. And the way we capture this level of accuracy is called the confidence interval. So you say like there's like a 99% chance that the real proportion P is in this range, and then there's that 1% chance that the real answers, even the tails, is too high or too low. So let's do one example of this backwards version, and then we're going to do more on Monday. So let's say that an airline has over 2,000 planes, and they wonder what proportion need new windshield wipers. Okay, and you might think it would be easier just to say, well, let's check every plane and see which ones need new wipers and then replace them. But it might just be too much effort to check all the planes. So it'd be easier to just check a few planes, get an idea of what proportion need new wipers, and then the people in charge of buying wipers can just like make sure that they buy enough. And then they might have a few extras, but they should be pretty close, assuming their estimate is decent. So instead of checking all 2,000 planes, they randomly select 150 planes to check. Why 150? Well, I just picked the number 150. The more they check, the better their estimate's going to be. 150 seems like a solid number. So I just picked that. So this is the experiment they run. They check 150 planes, see how many need new wipers. So out of the 150 planes, 39 need new wipers. Let's find a 95% confidence interval for the proportion of all planes that need new wipers. Okay. So we're going to try to find a range which we think that there's a 95% chance is going to contain the real number. Okay. So we're going to do this entirely in Minitab. I'm not going to do another normal distribution here. I am just going to go to Minitab and use its confidence interval computer and see what we get. So let me flip over to Minitab and show you how to do that. So let's bring up Minitab again. Okay. So how do you do a confidence interval? So this is in a new tab. It's under stat. So we go stat and then basic statistics. There's a whole bunch of options here. We want to use one proportion. Okay, so we are estimating a single proportion. There's going to be basically like a whole bunch of the stuff on this list we're eventually going to do. Right now, we want to estimate one proportion. That's how our question is set up. Now, there's different ways that you can enter the data into this. One way is down here in this table, we could have the results of the individual checks. We could have 150 sort of like yeses and nos in this table. And in real life, like maybe that's what you have. Like you have a spreadsheet full of data and you want to run an analysis on it. Well, this time someone has gone along and counted things up for us. They counted how many yeses you need new wipers and how many no's you don't. So one or more samples in each column, that's not what we have here. That's when you have the raw data in the column, the yeses and no's for 150 different results. What we instead have is the summarized data. So in this little drop menu, we choose summarize data. So how many events were there and how many trials? So trials is the number of planes you checked. That was 150. And events, that's what I've been calling successes, like how many times, each time you tried the thing, how many times did the specific result you're looking for occur? That's number of events. So I said it was 39 out of 150. So we had 39 events, I've called successes in the past, out of 150 total trials. There's a hypothesis test thing here. We're going to talk about that next week. We aren't up to that. We do want to make sure that we are finding a 95% confidence interval. So where we think there's a 95% chance the real proportion is, and only a 5% chance that it's not in that range. So let's click on options. And the default is 95%. So that's sort of the industry standard. There's a thing about alternative hypothesis here. That's for hypothesis testing, which we aren't doing yet. The last one is, do we want to use the normal distribution approximation or choose exact, which means do we want the computer to use the binomial distribution? Well, traditionally, stats has been done with the normal approximation because that's what we have tables for. That's what people can handle. But now that we have decent software, the software can do stuff that normal humans calculating things by hand couldn't really handle. The binomial distribution is more accurate to use. That's what it means by exact. And in the past, I've chosen normal approximation because that's traditional and maybe our textbook even uses that, but exact is better. We don't really have a good reason not to use exact. So I should say that like, if the answers you're getting are slightly different than answers that I'm listing or ones from the textbook, it's probably because they're using the normal approximation instead. The exact answers are more accurate. So this is because you're not doing the normal distribution approximation. Okay, so we're going to use exact. Hit OK, see what we get. So 39 out of 150, they give us the sample proportion. That is the proportion, what I called p hat before. The proportion in our sample was 26%, 0.26 of the airplanes we checked needed new wipers. And then confidence interval is 0.191876 to 3378. So I'm going to copy this over to Word. Let's go back to Word and talk about this result. So this is the result that I got. Libri 16. So this is the result I got. So our 95% confidence interval, 95% confidence interval. I'm going to use CI for confidence interval just as an abbreviation. Is 0.191876 up to 0.337857. So basically, we don't know what proportion of all the planes. And I said 2,000 planes, but it doesn't. The 2,000 doesn't really come into this. You know, they could have had 100,000 planes. What we're saying is that there is a 95% chance, and sometimes we say we are 95% confident. So that's sort of like jargon. So there's a 95% chance the true proportion of all planes that need new wipers is between 0.191876 and 0.337857. Now that's a pretty wide range from like 19% to 34%. If purchasing wants to make sure they have enough wipers, they better buy enough to cover 34%. And if they want a tighter range that isn't like 14% wide, they have to sample more planes. That's the way you narrow the sample, is you do more. So this video is getting a little long, so I'm going to cut it off here, and I have one more to talk about in another video.